We are now ready to start with the second lesson of our algorithm analysis module. In this lesson, we will look into an important topic under algorithm analysis, which is called the big O notation. We'll also discuss its meaning, both in terms of math, and we'll understand it via graphs. Now, a little bit of background for this notation. It's the most common method and notation that's used for discussing the time complexity or runtime of algorithms. What Big O says is, how does the running time of an algorithm change, rather increase or decrease, as a function of the amount of input data passed to the algorithm? And it's denoted in shorthand as a big O sign followed by some numbers that will go inside brackets, and basically it gives the asymptotic execution time of the algorithm. Here is the mathematical definition of big O. It says that T of n is big O of f of n if there are positive constants c and n0 such that T of n is always less than or equal to c times f of n when n is greater than or equal to n0. Here, n is the size of data input that's passed to the algorithm. T of n is the actual running time of the algorithm, and f of n gives an upper limit or upper bound on the running time of the algorithm. Note that it's an upper bound specifically, and c and n0 are just constants. It helps a bit to understand this in terms of graphs and explaining in terms of plain English language besides math. So if we plot the definition of big O in terms of a graph that I show on the right hand side here, this is what it looks like. So the curve plotted in red is T of n, the actual runtime of the algorithm. The curve plotted in blue is another curve that gives the upper bound for the runtime of the algorithm. And c and n0 are constants. Here I have c equal to 1 and n is this value n0 shown by a dotted vertical line. So in English what this says is we have to find a function f of n that is given by this blue curve. Find this function fn and constant c and n0 such that when n is greater than n0, or in other words, whenever we are to the right of this dotted line on the x-axis, then T of n, the actual runtime, or the red curve, is always less than or below the blue curve. If that condition is satisfied, then we can write Tn is big O of Fn. In other words, if you just look at this graph, Tn is never able to cross over f of n, intersect and go above f of n to the right hand side of n equal to n0. So in other words, fn is kind of forming a ceiling or an upper bound on T of n. In that case, we say Tn is big O of fn, or Tn is upper bounded by f of n. Let's take a few examples to understand this concept. Let's say that T of n, our algorithm's runtime, is given by n square. And there's another function given, f of n, which is n4. The question is Tn is big O of fn. Is this statement true or false? To go about doing this analysis, we will take the same approach we had taken on the previous slide to understand the definition of big O. We'll go ahead and plot a graph. Okay. So the red curve once again is the running time of the algorithm Tn, and that's the n square curve. The blue curve is n to the power of 4 curve. And as you can see here, if you solve the intersection point, these two curves intersect at n0 equal to 1. And to the right hand side of n0 equal to 1, when I said c equal to 1, to the right hand side of that, fn is always above T of n. So I can rewrite that in math as for c equal to 1 and n0 equal to 1. In other words, we have found constant c equal to 1 and n0 equal to 1, such that whenever we are to the right hand side of n0, whenever we have n greater than or equal to n0, n greater than or equal to 1, we have T of n is less than c times fn, which is basically the definition of big O. So the answer to this question is Tn is in big O of Fn. So that statement is true. Let's take another example. Let's keep the running time of the algorithm the same, n squared, and let's now change our curve f of n to 2 to the power of n. So now the question is Tn in big O of Fn? Is that statement true or false? So once again, we plot curves as before. We solve for the intersection point, setting c equal to 1. And if you solve this, you will see that these two curves intersect at n0 equal to 2. Okay. And if you look to the right-hand side of this, note here now, the red curve is on top, Tn is on top, and the blue curve, 2 to the power of n, is below it. So this translates in math to, for c equal to 1 and n greater than or equal to 2, Tn is greater than or equal to c of Fn, which is not the definition of big O. Big O says that Tn must be less than c times f of n. So it looks apparently that Tn is big O of Fn is false, because the less than condition was not satisfied here. But watch out for a common mistake here. If you plot these curves further for larger values of n, you will see that they intersect again, and this time at n equal to 4. And for all values of n to the right side of n0 equal to 4, that is greater than n greater than 4, you will see that Tn, the red curve, is always below the blue curve. Okay. So indeed, we get for c equal to 1 and n greater than or equal to 4, Tn is less than or equal to c times f of n. In other words, this is the condition for big O of n to be satisfied. So Tn is big O of Fn. That statement is actually true. So this example illustrates an important point to keep in mind, which is when you are solving for the curves Tn of Fn to figure out whether they are related by big O or not, it's important to find the rightmost intersection point, or the largest value of n for which those curves intersect. Okay. If you do not find that, then you cannot make a claim whether Tn is below of Fn or whether it's the other way around. So keep in mind, you have to find the rightmost or the largest value of n for which the curves intersect. Okay. Let's look at a third and final example for big O. Here, once again, I have Tn and Fn as two different curves. Tn, runtime of my algorithm, is n, and f of n is 2 to the power of n. Okay. Question is it true or false, like before? And so as before, I plot the curves. The red curve is t of n, runtime of the algorithm, and f of n is the blue curve, 2 to the power of n. So here, as opposed to the previous examples, you see that these two curves are never intersecting. Okay. But still, we can make a claim that for all values of n, we have Tn is below f of n. Or in other words, the condition for c equal to 1 and n greater than 0, we have the condition Tn less than or equal to c of Fn satisfied, which means Tn is big O of Fn. That statement is indeed true. So the point that I want to highlight here is, as opposed to the previous examples where we saw that the two curves did intersect, in this example, the curves do not intersect, but still for all values of n greater than 0, we have been able to establish, or the curves have the shape that Tn is less than c of Fn. So once again, reminding you, the curves might not intersect, but still the condition that for n greater than some value n0, you should have Tn less than c times Fn. That condition should remain true for the big O notation to be valid. So summarizing, in this lesson, we looked at an important definition that's relevant to algorithm analysis. It's called the big O notation. We looked at the math definition of that. We looked at the graphical equivalence of that math notation. And then we solved a few examples illustrating important cases to find out whether the runtime of the algorithm, which is denoted by t of n, and another curve given by f of n, whether they're related by big O or not. So this concludes this lesson. In the next lesson, we'll look at a few other notations for denoting the time complexity of algorithms besides the big O.